Let me start by thanking the organizers for the opportunity to speak here at IPAM and for putting me after lunch to give me the challenge of trying to keep all of you awake. So my talk is non-hydrodynamic phenomenon near plasma interfaces. And in the spirit of this workshop, as we heard this morning, many of these talks are on very different topics. And looking around the room, I'm guessing most of you don't work in the fusion community. So what I'm going to do is start off by talking about dense plasma interfaces in the context of inertial fusion energy, just to motivate the problem that I'm going to be talking about. And then you'll see that the geometry that we found important in this context for this application is somewhat similar to some of the geometries that we've already seen in the talks that preceded me today. And then I'll move into sort of some background on how people model these fusion experiments to design them and try to get them to work, and what the problems are that leads us to attacking it from a more microscopic, stochastic, many-body perspective. And then I'll talk about our model, and I'll show a lot of numerical results from that. So that's sort of the itinerary, what we're going to do. So let me start by motivating the problem itself. Some of you may or may not know that humanity had a big achievement in the last few years. This is a paper that just came out in 2024. We finally reached ignition in the laboratory. There's many, many papers on this topic. This is just one of them. And it says achievement of target gain larger than unity. There's something, as they point out, we've been waiting for many decades to be able to achieve this, and we finally did it. And this achievement was done on December 5th, 2022, at the National Ignition Facility, which is at Lawrence Livermore National Lab, up the state from here. And this has driven enormous amounts of excitement, because now that it's proven that this can happen, lots more money is coming into this. Different funding agencies have jumped into the game. Startup companies have been formed all around the world based on this result. And so it's exciting times if you are working in this area. So what does it look like in terms of the experiments relative to the experiments that you guys think about? This is, let me start here on the right. This is NIF, National Ignition Facility. This is a few football fields laid next to each other, just to give you a sense of the size. You can see the size of a car. And in this cylinder that you see here that's labeled target bay, that entire target bay right here is this photograph on the left. Some of you might recognize that it was used in a Star Trek movie, so it might look familiar to some of you. But this is the target chamber. All these lasers that are here, these large lasers, are all funneled through all of these channels, come down in through here, and hit a target that's very small. So one of the big differences in these types of experiments, maybe to the ones you're used to, is the experiments are very tiny and they don't last very long. And that makes them very difficult to diagnose, and that means that we rely very heavily on modeling. So we have to try to get our modeling right, so that our codes that we use to design these targets will work, and clearly progress has been made, as you saw with that paper. So that gives you a sense of the scale. Since then, people realized that numerical simulations did play a big role in making this work. So there's a paper by a handful of people that led the computational effort. The design code that they use for these types of experiments is called Hydra, also developed at Livermore. I've seen a talk on this actually right here once. And so it's known that these models that we're building are very important for those reasons. So you see the size of this. Few football fields getting compressed down into, this is a ladder, so you get a size of a human, into this, and then those get compressed down into something that's the size of like the tip of your finger. Okay, so it's a lot of focusing of laser energy onto a target. Okay, and if you read the fusion literature, there's two types of fusion, this type of fusion, indirect drive and direct drive. If the laser hits the target directly, that's obviously called direct drive. The Omega Laser Facility at University of Rochester is an example of that type of approach. At Lawrence Livermore, where they achieved a gain of excessive unity, it was done with indirect drive. And that's what you're really seeing here. And the idea of indirect drive is the lasers come into this little can. This can is called a hohlraum. And that radiation comes in, and it's focused not on the target, but on the walls of the hohlraum. Okay? And so it heats this, which is usually some high Z element, gold or something like that. It could even be uranium. And those are converted into X-rays. And those X-rays bathe the surface of the capsule, which ablates away from the heat, and therefore has the clever name, ablator. And by the rocket mechanism, if the ablator is ablating in this direction, by conservation of momentum, it's going to drive a shock inward and compress the fuel. And if you see the cross-section here, the fuel for thermonuclear burn is deuterium and tritium, at least on Earth. The sun uses protons, but we use DT. And here's, this particular design has a DT ice layer. It's cryogenic. And then there's a DT gas field inside of that, and then that gets compressed. There's other designs, but, and they're always fiddling with that. That's why they need these design codes, and they need to understand this physics well to be able to do this. You can imagine diagnosing this. This capsule does not last very long, and you're not going to fit very many diagnostics into this little can. So you rely on what you can do, and a lot of it relies on modeling capabilities. Okay, so what happens in terms of the material science inside of that capsule? This is a temperature density plot. So this is temperature and density. Notice that it's a log-log scale, right? So most of the material science you do is at a fixed point, solid density, room temperature, or something like that. What happens in these capsules is they start off, like I said, they start off cryogenically, so they're very cold, and they're around solid density. The gas is gas, the DT ice is ice. So there's a little bit of a variation in the initial density, but as the shock comes in and compresses the fuel, it obviously needs to heat it. The sun is about 1 keV temperature, so that's sort of the target temperature that they try to get at. Here on Earth, we can exceed the sun's temperature because we need to be more efficient. We don't have a gig a year, we have a nanosecond. So we try to get pretty hot. And so you can see that here. You can see it starts off, this is a track of an ICF capsule. Starts off cold and at some density, and then because of those shocks that are going in, you see it's compressed. It's going to higher density, much higher density, exceeding an order of magnitude of compression. And it's going up many, many, many orders of magnitude in temperature because you've got to achieve a temperature high enough that you overcome the Coulomb barrier for DT fusion. So that's the basic idea. So from our perspective as modelers, all of our models have to work across orders of magnitude in density and many orders of magnitude in temperature. So it's one of the challenges we have. Any model we have that we build automatically has to be extremely flexible. And as you can see from just the words on here, you have solid, plasma, gas, and so on. So the models need to be able to span different phases of matter to be able to work well. And the codes that are used to design these capsules need to be aware of basically everything that's going on in this plane. So it's a big computational challenge. Here's some plasma parameters. Some of the plasmas might be strongly coupled. Some of them might be weakly coupled. Keith talked about the Vlasov equation. Those would be weakly coupled plasmas, which would be up here on the upper left side of this line. Strongly coupled plasmas would be down here. If it's strongly coupled enough, it crystallizes and becomes a solid. Similarly, something we very much care about is whether the matter that's in there is quantum mechanical or not. And as you go up this ICF track, it's going to span that whole region. So you start off below the green line, and it's quantum mechanical, and then as you go above this line, the plasma eventually becomes classical. So again, the models need to span quantum, classical, strongly coupled, weakly coupled, all these things. Okay, so that's sort of gives you a sense of what our challenge is. Okay, so what do they use now? If you wanted to model one of these experiments, they don't use these equations because these are a little bit too simple, but they're close enough to get the idea. These are obviously the deterministic hydrodynamic equations, at least a version of them. And it would be nice, in principle, if you could use a model that looks like this. And they do use models that are similar to this. If you look at this in detail, what you see is that you have one density. So you're wrapping up all of the particles as a density variable, right? And that makes it efficient because you have one continuity equation for the material, okay? This might seem obvious, but I'm going to deviate from it in a minute. Okay, and then same thing here. There's one momentum equation for the velocity of the fluid and the density of the fluid, okay? And that's nice because people that write these hydrocodes don't want to write hydrocodes with multiple momentum equations, okay? And most of the codes won't do that. Some of them do, some of them don't, but most of them don't. And then similarly for energy, energy can be quite complicated because you might have energy in photons. Typically the electrons and the ions are not at the same temperature, so you have to track that separately and their time evolving. And maybe the ions are also at different temperatures. Now they're kinematically coupled because of their similar mass, which is something you want to check. Okay, so that would be nice if this were true, or something similar to it were true. So let's think about what our particular problem is in that context, okay? So people are using these sort of single fluid equations to model these experiments. And here's what can happen. If this ablator material mixes with the fuel, it will cause the fuel to cool. And you're not going to get ignition, you're not going to get gain. And the primary reason for that is that here, this ablator, like I said, it's typically a higher Z element. Here I'm showing diamond, like a carbon. They often use plastic, so there could be carbon and oxygen. It could be a glass. There could be silicon and oxygen in that ablator. Depends on the shot that they're doing, but it's not hydrogen. It's higher Z. And so if this layer, the ablator layer, mixes in here, that would spoil the ignition that we're trying to achieve. And as Keith pointed out, one of the things he and I are interested in is turbulence. And so one possibility is that this interface right here, as it's pushed inward, you can see it's high mass pushing on low mass, so it's Rayleigh-Taylor unstable. That could cause a transition to turbulence, which would mix the ablator into the fuel. What we're focused on here today is what's called atomic mix, is just the small scale diffusion of particles in here, okay? Now what happens if by either mechanism, turbulent mix or atomic mix, what would happen? What would happen is these higher Z elements would get into the fuel and they would radiate. So the free electrons, because now this is ionized, those free electrons collide with those high Z species and they emit bremsstrahlung. And the X-ray part of that bremsstrahlung is transparent to everything around it, and they just carry energy out and cool the fuel. So this is the last thing that you want to have happen. I sort of give a scaling here that for a deuterium-tritium carbon mixture, you can see that the bremsstrahlung with mix has this Z squared in it, which is a factor of 36 times more bremsstrahlung for an equal density than you'd have if you didn't have that mixing process. So it's extremely important to not have mix from the ablator into the fuel. So in fact, that's why we have a separate effort at University of Rochester for direct drive, and then the separate one for indirect drive. If you do indirect drive, like they did at Livermore and achieve ignition, those X-rays that come off of the hull ROM are very homogenized. And so they heat the outer part of the capsule more uniformly, which causes the compression to be more uniform. Therefore, mitigating a lot of the hydrodynamic mix, turbulent mix that you might get, okay? So that's the question, is how much of this ablator material is mixing in with the fuel. This would obviously, hopefully I've motivated this, would be impossible to measure directly, right? And you can also see, if you look at these equations, let's suppose that those guys at Livermore are solving equations like this. These equations don't allow for atomic mix because all of the species are locked into a rho and they're locked into a V. All the species move at velocity V, and they're in some mass density rho. And so this wouldn't describe the process that we're interested in looking at. Okay, so what would you do? So one thing that you can do that's the easiest thing to do, and they did this, is they said, well, that's easy. We don't want to separate these two equations into multi-species because computational efficiency reasons. But if we're looking at atomic mix, we have to take this equation here and we need to separate it and make it multi-species. So now there's a subscript S on these. And obviously, you're all math people, these equations are now not closed, right? Because now you have too many velocities in this equation and you only have one velocity that you're actually tracking. So you have a closure problem. So how do you deal with that closure problem? Well, you introduce, the easy way to do it is you introduce transport coefficients. So what you do is you hypothesize that this velocity is associated with a current of each species, and the current of each species is given by gradients of variables that you know, so that the equations are closed, and transport coefficients. This is where transport coefficients come from, like viscosity and these kinds of things. And so what you could do is you could just take those equations and write them in a way, so you introduce in this example what's called the interdiffusion coefficient and the thermal transport coefficient. And then the burden goes on people to be able to compute these two coefficients accurately across all orders of magnitude of density and temperature for all of those different species. And if you had tables that would allow you to do that for these conditions, you'd have a really good model that's computationally efficient, but it allows for the possibility of atomic mix. So what we did in the early days, you can see this paper here, is we did that. We developed all these transport coefficients and published those. These are the transport coefficients that are in Hydra that was used to achieve ignition. And then later, we improved upon this model using machine learned potentials to make it so that there were more accurate material science physics in those potentials. And so those are obviously available too, but I'm not going to talk about either of these in this talk. But this is what sort of the machinery that you would use if you're going to take this particular approach. Okay, so when we approach this problem, after solving it at this level, what we asked ourselves was, are those hydrodynamic equations correct? Are the momentum equations locked? Can we use one momentum equation? Is the transport as simple as diffusion? There could be anomalous diffusion. There could be all types of fluctuations that hydrodynamics simply doesn't capture at all. Okay, so that's what we wanted to be able to do. And so, all of you know the challenge of this is if you want to answer those sorts of questions and you can't rely on experiments, you're going to have to do a simulation of some kind. And obviously that simulation is going to be a lot more expensive than the one you're doing because it's going to be higher fidelity because it's what you're using to validate the lower fidelity model. So it was a big challenge. And so the idea was, can we think of a computational method that makes as few assumptions as possible? It needs to span really large length scales. I mean, a micron for us is quite long, and many tens of picoseconds to allow the mixing process to actually occur. And as I've hopefully motivated, you have to describe matter across these many different phases, possibly with many, many, many species. So, the easy answer to this, of course, is use molecular dynamics to do this. And if you just do like a naive calculation of what it would take to do this using molecular dynamics, you would probably be locked up because it would be crazy to attempt to do something like this. So what we did is we built this multiscale model that allowed us to break all of the bottlenecks that would prohibit such a calculation, which I'll describe to you now. So one of the things that we needed to develop, which I won't go into too much detail about, but we developed it, was in contrast to maybe some of the electrochemical systems you look at, the ionization state is changing in time and space, right? So since the system's heating, it's obviously becoming more ionized. So we don't know a priori what our charge states are. It's also highly compressed matter that's getting compressed to higher than solid density. No one's ever measured those ionization states before. So you've got to be able to predict ionization states in highly compressed, very hot matter. And because we're looking at a mixing process, the ionization is occurring during the simulation. So you can't calculate the ionization and fix it. You have to keep recomputing it because the mixing itself changes what the ionization states are. So first thing we had to do was develop a spatiotemporal ionization model that spans all temperature and density for all possible species. And that we did using orbital-free density functional theory, which, like I said, I'm not going to go into that part of it. It's a whole separate talk, but we did that. Okay, and then to do the extreme variation in material properties, like I said, we have our simulations use 5 species, and as they evolve every single time step in the molecular dynamics, the new material properties are updated self-consistently with the new ionization state. We regenerate new potentials. We compute all the electric fields in the macro cell, and then go to the next time step. Okay, one of the almost impossible problems to solve for any of these types of problems is dealing with the electron-ion mass ratio. Now, most of you would say, well, that's easy. That's the easiest part of this because you're just going to use the Born-Oppenheimer approximation like every other DFT code. But here we can't. And the reason that we can't is that the Born-Oppenheimer approximation is not valid for these systems for a couple of reasons. It's like almost valid, so we can cheat a little bit, and that's what helped us. But there's 2 examples of why this is slightly breaks with Born-Oppenheimer. One of them is the fact that the energy that comes in from when the laser hits the ablator, the first heating of that interface comes from radiation. And radiation is primarily absorbed by electrons. So automatically you have a 2-temperature system with energy being sourced into the electrons, and those electrons then need to dynamically heat the ions. So as I show you later in the simulations, as the ions are heating, remember they're being heated by the electrons that are having the energy sourced into them. Furthermore, it's possible to generate fast ions. And of course, our ultimate goal was to simulate fusion. And if you're simulating fusion, you are going to generate very fast alpha particles as part of the fusion process. But you could also generate fast particles, as I'll show you, just because of the interface itself. Because the interface itself will generate a large electric field, and you have basically what's called a stopping power problem, where you have a fast ion that's generated, and why does it slow down? Because of the electrons. So the electrons need to be active in this model, a little bit past Born-Oppenheimer, but not completely dynamical, so sort of half Born-Oppenheimer approximation. So that was another part of the model that we needed to deal with. And then, of course, if you're going to do diffusion across one of these interfaces, you have to have a simulation that's large enough to do this. And of course, these are fairly expensive. The overall electron density is done with our own custom density functional theory using various orbital-free methods. We use orbital-free methods so that we can span the entire temperature range quickly relative to cone sham. And all of those are expensive, and so you have to be able to do that over a very large length scale to be able to see this phenomenon. Okay, so here's how we picture it before we get to the actual simulation. So here's that capsule design, one of them. And then what we did is we said, okay, we're going to try to simulate this interface by setting up an MD simulation of order a micron in length for tens of picoseconds that spans this gap, okay? So on one side of the simulation is ablator materials, and on the other side is fuel, DT, deuterium and tritium, okay? And then that's what we want to simulate. So the way we did that is we did this. Like I said, we developed a multi-species ionization model. You can look on our paper if you care. Everything was done with orbital-free density functional theory. We tried several, just for validation purposes, and that worked quite well. I'll talk about our electron model in a minute. We use like a Langevin approach, but I'll show you that in a second. And then we use a simulation cell that was like I call it here a pencil-shaped simulation cell. So to be able to span a micron, we have this very long simulation cell that's really thin, like this, but it's periodic in this dimension. So it mimics a bulk in this direction, but it's not very big in this direction, because that's not what we care about. In this direction, it's long so that we can actually watch the diffusion occur. Okay, so that was sort of a trick. This was done a while ago, so we could only use about 50 million particles. Okay, so the way we built this into a multi-scale approach to get all of those working parts to actually work together was with this scheme, okay? And I'll start here at the bottom. Imagine what we do is we have our simulation cell, and we break it up into zones. In each zone, we solve the atomic physics problem, which is the multi-species ionization problem. Once we know those charge states of the ions, we can put those into a Poisson equation of some sort, and that gives us the charges on those ions, okay? Once we've done that, we then know how many free electrons there are, and we let the free electrons float through the entire simulation cell, and that's a DFT calculation across the 50 million particles, okay? So they can float. So if an electric field forms in the simulation cell, great, that will happen automatically and self-consistently, okay? So that is this macro scale where we solve that DFT problem. Then once we've solved that DFT problem, we can then go back down to the atomic level, and we can ask whether or not that in that cell there's an electric field or not. If there is an electric field, we allow it to distort the local atomic environment, which generates these asymmetric potentials between the particles. So the particles away from the interface look basically spherical plasma-like, but as you go towards the interface, all of the potentials are tilted because there's a strong electric field there, and then as you move away, they become more spherical again. So we include all of that physics in this model automatically, and then every time step, recompute the atomic physics, float the free electrons, do the DFT calculation, compute the potentials again, and then do an update for 50 million particles. Okay, so this is what it looks like. This is our pencil cell. This is half of the pencil cell. This is actually the middle. And you can see it's long and thin. You can see there's an interface. This is the interface blown up once, and then this is a blow up of the blow up. So you can kind of zoom in. One of my co-authors was riding on a van to work and back to Livermore, and one of the guys in the van worked on the capsules for NIF. So our stoichiometry that we picked was the design they were using at that time. And what it was plastic and DT. And so what you see here is the DT, as you can see, is red and purple. So this is the DT fuel. This is all fuel. That's that DT ice layer. And then here the green, or what looks mostly green, is actually green. And the yellow here is impurities of oxygen. And then there's some hydrogen in there. I don't know if you can see the blue because it looks like the purple, but there's actually 3 species in the plastic, and there's 2 species in the fuel for a 5-species simulation, okay? That's what it looks like. And then, as I said, every time step, this is binned up, atomic physics calculation, DFT calculation, new potentials, update with the forces, and then just keep repeating that until we get what we need. Okay, so that's what it looks like. Okay, so let me go to the electron model. So the electron model, like I said, it's kind of quasi-Born-Oppenheimer, right? So most of the forces that we're going to deal with come from that DFT calculation that I described already. But those are static, and they don't allow the electron temperature to change or source energy into the ions, and they don't provide drag directly on the ions. So the way we handled that is we said, okay, we need to describe what we call temperature relaxation, which is electrons heating the ions, and stopping power, which is slowing down fast ions. Those are the 2 physical processes you want to describe. So what we did is we looked at various models and settled on what's actually a fairly simple model, which is this well-known Langevin equation. We could have done something more complicated, but this actually did what we needed it to do. So what we did is we took the MD forces that come from that DFT, and then we add to it the usual fluctuation dissipation terms in the Langevin equation, as you well know, and said, okay, this is basically the equation of motion for the ions in the presence of the electrons. So the electrons are the bath, and the ions are our system. So this is a system equation. These are internal system forces, and these are bath forces, if you want to think about it in sort of a Mori-Zwanzig sort of a idea. Okay, so that's what we did. And then you can solve this equation. It's easy enough without the MD forces, and you get something that looks like this. And you can see that what it does is whatever your initial velocity is, it will eventually decay on a time scale, which is 1 over gamma, right? And so if you somehow knew what gamma was, you could put that in your MD code, and then those ions would slow down due to the drag they feel by moving through that electron bath at the right rate. Okay, so there's a question of how to determine that. Okay, and then you have, obviously, you have a noise term, and if all of you probably are experts on Langevin, this is the noise term that keeps the velocity from ever going exactly to 0. And of course, that's responsible for keeping the ions at a finite temperature and not cooling down to absolute 0, right? And this term here, the noise term, is crucial for getting the temperature right, okay? So how do we do that? Okay, so what we do for that is simple. We take the velocity and square it and take the time derivative instead of just, here I have dv dt, here I just have dv squared dt, simple. And then I stick in Langevin. You could go through the math, but it's all well known. And let me just go to the bottom line. The bottom line is the kinetic energy of an ion will evolve like this. It will decay in that same time scale with a factor of 2 because of the squared. And it will go from some initial temperature, wherever you started it, and because of those fluctuations, the eta, the noise term, it will eventually go to some final temperature that might be different, right? And so for us, that is definitely the case because our ions are cryogenically cold. It's DT ice. And the final temperature here is whatever the electron temperature happens to be at that moment, because that's where the energy is being sourced into the simulation, okay? So for us, these two are crucially important to keep different because they're causing the heating that we're interested in looking at. So pretty simple model mathematically. And then we have to turn to plasma physics to determine what these coefficients are. And so just quickly, because I know most people in here probably are not plasma physicists, but what we did is we write down, this is the deviation from Born-Oppenheimer. The electrons have their own temperature equation that we evolve during the MD. And we have expressions for their specific heat, their energy. We keep track of the thermodynamics of the electrons during the simulation and how they relax. And that is what causes the electrons to lose their temperature while they're heating the ions. Okay, and then we have expressions for this tau. Now, the way we get that tau is we actually look at how the ions are responding to those electrons, right? So this is the system, and there's a bath. So it's like a Langevin type model. And what we say is the ions feel a drag on average because they're moving through this electron fluid, okay? And so they're going to slow down in proportion to this parameter and linear with respect to the velocity, okay? And if you've ever studied stopping power, this is a low velocity stopping power formula. You can go to the literature. We happen to pick this one. And this is a stopping power model for ions moving through high density matter. So it's sort of designed for what we wanted. And so we could take this model, which includes Fermi-Dirac statistics and all the quantum that we need, that spans the entire temperature range that we care about, and we can basically match that particular model to this stopping power and figure out what this gamma is, put that into the Langevin equation, and then with the fluctuation dissipation theorem, we've nailed both of those terms, and we have a new semi-dynamic electron model, a little bit beyond Born-Oppenheimer, okay? Okay, so let's look at some results just so you can see what all of this does. That's what sort of a blizzard of what the model is like. So when we set this up, we talked to the people at NIF and asked them, how does this interface get heated? And they said, we don't know. So what we did is we sort of talked to them about the shock coming in and how much the radiation precedes the shock as it's coming in and sort of bathing that interface and sort of glean some scenarios. So unfortunately for you, this makes these plots more complicated, but it's fairly simple. There's two rows here. This one here assumes that it's called instant heating. So you can look at these as rows. This is the instant heating row. And basically what we did is we just said the electrons start at 50 eV. That's just our initial condition. The radiation came in, knocked the electrons up to 50 eV. Through that temperature relaxation phenomenon, they will heat the ions up at rate 1 over gamma, IE, and then everything will start to happen. Because the ions are heating, they'll start to move, okay? Here, what we did is we have a ramp that takes the electrons and ramps them up from 0 up to 50 which is sort of modeling the fact that the radiation may start off less intense and become more intense as the shock comes in. Neither of these are particularly well known, but the NIF people thought that this was reasonable. Okay, so you can compare this is instant heating, and this is what happens if things happen more slowly. And that's why there's 2 rows. Okay, so what you can see here is also the columns are time intervals. So this is what it looks like after 300 femtoseconds. And this is what it looks like after 10 picoseconds. So so early time, but not initial time because it would be boring. And this is the later time. Okay, so what do you see right off the bat? So there's some interesting things that you see. The vertical gray line that you see here is where the initial interface was. Okay, so one of the first things that we noticed is that when we started looking at these plots, where you would put the interface, like here or here, was not where the interface was supposed to be. And of course, there's an obvious reason for this. It's an equation of state effect. Right? The plastic is under much higher pressure for a given temperature, and it compresses the fuel instantly. As soon as that fuel gets hot, it pushes on the fuel, and it moves the interface over until you get a pressure equilibration. In other words, the interface moves until the DT pressure goes up to match the dropping plastic EOS pressure. Okay, so that's what happens. And you can see it most clearly here when you have this instant heating, as you see it drives a pulse. So as soon as that interface heats up, the plastic compresses the DT and launches a little wave or shock, whatever you want to call it, into the fuel. So the interface does that all by itself before the main shock even arrives, because this has been caused by radiation, something that no one had ever seen at the time. Okay, so other things that you can see is the species do separate, but in a complicated way. If you look at all of these plots that you see here, the purple and red, remember what those are? Those are the Ds and the Ts. They're basically locked. So that single species continuity equation would have been great, right, for them. And of course, the reason for that is they're same density right next to each other, and they have very similar masses. So you kind of expect that. But if you look at the plastic, you can see that the densities separate. And you can see that the hydrogen comes way in to the fuel. So the fuel region here is now DT with quite a bit of hydrogen in it, right? Which, again, no one knew that this might be happening at the time. And there's even a slight amount of separation between the higher Z elements, the carbon and the oxygen. Oxygen is the worst. It has the highest Z, but it's also at a fairly low concentration, okay? So those are some of the features that you see looking at the density, okay? And then you can imagine, if you're an if person, saying, good thing we put in a multi-species continuity equation, because clearly it's happening. But one of the questions that you might have just looking at these results is, sure, the species densities are separating, great, but how do we model it, right? Can we use standard transport theory, in other words, gradients of the densities in proportion to diffusion coefficients? So to do that, you have to look at more sophisticated properties. This is where things become very stochastic. Okay, so these are the velocity fields. Okay, and this is where things got to be pretty interesting. The first thing that you notice just by looking at these plots is none of them overlap, except for mainly the D and the T fuel overlap. And so that's consistent with what we saw with the density. But you can see that the velocity of the species, the hydrogen, like I said, the hydrogen separates from the plastic, if you remember. The hydrogen just leaves the plastic, okay? And when it leaves, it does it at very high velocity, relatively speaking, okay? So you can see that to model this with 5 species, maybe you could get away with 3 velocity equations. They would love to have 1. Probably don't need 5, but maybe 3, because the hydrogen is definitely decoupled from everything. The DT's locked, and we can just say that the oxygen and the carbon are locked. They look pretty close. Here, they're not very locked for this type of heating. So maybe here you need 4 velocity equations, okay? So we definitely are seeing a breakdown of the standard hydrodynamic models that they prefer to use. They probably weren't very happy about this. And then the other thing that you see that is interesting is that if you look at the velocity of the hydrogen here, it's going higher and higher and higher. It's like the hydrogen is just jetting out of the plastic and rocketing into the fuel. And then what you see is at some distance, it goes up and then it suddenly drops. Now, if you're a plasma physicist that studied stopping power, you'll recognize that's exactly what a stopping power problem looks like. You have a high velocity particle that's rocketing, and it basically shows what our drag model is doing. The drag model is working. You generate very high velocity hydrogens, and they feel the drag of the electrons. It slows them down, and they eventually will stop and presumably deposit their energy somewhere in here. That's how stopping power works. Okay, so from the point of view of looking at the velocity fields, we've definitely learned a lot of deviations from standard hydro, a lot of fluctuations. Okay, so let's look at the temperature. And the temperatures is very stochastic. I mean, we only have 50 million particles, so there's a lot of fluctuations in these simulations. So sorry about that. But one of the main things that you see, as I mentioned, is that you get these hot spots. So you have an interface here that's getting heated, and you have, if you could do it experimentally, you would see a region away from the interface that's suddenly very hot. Be kind of interesting. And that's because the hydrogen is getting rocketed out of the plastic, and at high velocity it goes in, the electrons slow it down, and it dumps its energy. So you have like a sort of an annulus or a shell of hot plasma inside of the interface, which is kind of an interesting thing to think about. Obviously, no one had ever thought about that before these simulations. Okay, so keep going. Okay, so then we asked ourselves, what's causing this hydrogen jetting? And most of the design codes that they use for IFE are hydro codes. Even though everybody knows, because the temperatures that we're reaching, that it's a plasma of some kind, warm dense matter, whatever you want to call it. There are no electric fields in these codes. There's no Poisson solve in these codes typically. So what we wanted to figure out is what's causing that hydrogen jetting, and it turns out that it's due to an electric field. So what happens is, let me see what's a good one to look at. Let's just look at the most extreme case, which is the upper left. So as this interface is heated, obviously there's plastic over here, it's higher Z. As the ions get the energy from the electrons, they heat and they start to ionize. The free electrons from the plastic, in our model, they go into the DFT calculation, they float away. Those electrons will leave and go over here because there's lower Z over here because it's hydrogen species, and that creates an electric field at the interface. Well, near the interface, because the interface has moved, okay? And those can be gigavolts per meter. They're extremely strong electric fields. And so this is what's responsible for that hydrogen jetting. If you work it out using just simple charge mass ratios, you can show that the lightest species will be the one that jets the most due to that electric field. And so what we see there is an electric field. Again, something that was not in their codes. And that's what's causing the hydrogen to go into the fuel, not where you want it. At least it's a low Z element. But the other thing that was good, there's a good news story in there, is that because the electric field is so strong, there's like sort of this check. There's like a check and balance here. The larger your electric field is, the more it will move ions around that interface, which means it rearranges the interface quickly, which means the electric field drops quickly. And so luckily, the higher the electric field, the worse your code is, but the faster it heals itself. Okay, so that's sort of a nice result. So so the last thing that we looked at was kineticness, and so the extreme is that the hydrodynamic equations, no matter what, don't work. So hydrodynamics come from moments of kinetic equations, as Keith beautifully described in his talk. What if you can't use moments at all, right? So we wanted to test for that in this particular context. So we made up a bunch of different metrics for kineticness. The one I'm showing here is just this particular moment ratio, v to the fourth divided by v squared squared, okay? And you can make others, and you can figure it out for 1D flow 1D flow versus 3D flow. There's some constants that go in here. And we adjusted all of that so that if it were hydrodynamic, and therefore, or sorry, Maxwellian and therefore hydrodynamic, it would be unity. So that's how we adjust it. That's why these are all 1. So any deviation from 1 here is a deviation in this ratio telling you how non-Maxwellian the interface actually is. And of course, if you cared about this, if this were a factor of whatever this goes to above 2 was important to you as an IFE modeler, you would have to think about improving your code to be able to handle kinetic effects, which would be going above the temperature equation somehow. Maybe not a full kinetic code, but maybe higher order moments. Maybe you need several other moments. The other things that we looked at, which I don't show here, is we could also look at parallel and transverse temperature. Because it's a full MD simulation, every piece of information was accessible to us to look at in terms of kineticness. And we can see here that it is roughly hitting some kinetic regions. So it's not hydrodynamic at all times. So okay, so with that, let me just summarize. We've been examining these IFE experiments that have been showing a lot of success lately. We developed a multiscale model with spatiotemporal ionization and these OFDFT force fields using pencil 50 million particle simulations. We have this sort of new quasi-improved Born-Oppenheimer where we can do temperature and momentum relaxation even within sort of a simpler DFT approach. We did a bunch of simulations for this long micron scale and looked at a bunch of different quantities that I just showed you, and we see some important deviation from hydrodynamics that might be important to these designers. And so just to end, I want to thank my collaborators for this and thank all of you.